All right, so in this video, we're going to start the second section of chapter 11, and I believe we're going to do 11.2 and 11.3 we might just do together. Um, so we're going to start talking about constant volume and constant pressure and constant temperature processes and how that relates to the amount of heat that's given off and changes in volume and pressure and so on. So, process and how that affects work. Processes that change a system's thermal energy are referred to as any thermal process, and that ought to make sense. So, if you're changing the thermal energy, that's a thermal process. If it occurs while the volume remains constant, then we call that a constant volume process. And so you can see an example here below. So we're in the type of container where we cannot expand the volume out anymore. So we have an initial pressure, we have heat that's added into the system, and then we have a final pressure. Okay, let's move this up here. Come on. There we go. All right, so adding thermal energy into a constant volume process increases the pressure because there's no work, there's nothing, no displacement of the walls. So we're not moving anything. So no work is done in this process. And that's important for you to remember. You may have to do a little more memorization with these than normal. But so in a constant volume process, the volume increases the pressure. No work is done in the process because there's been no displacement or no movement of the walls of the container. So we set work equal to zero. And that means for our first law of thermodynamics, that means that the change in thermal energy is just equal to the amount of heat that's added. So for constant volume processes, remember, no work is done. We are only changing the energy, the thermal energy, and that is equal to the amount of heat that we wind up adding. Okay. All right, so processes that occur while the pressure remains constant are called constant pressure processes. So this particular diagram is showing you what it would look like for a constant pressure process. Thermal energy is added to the gas in a container under fixed pressure, and that pressure does not change. So what happens is the volume will change when we add the heat. So the container in the figure has a gas that has a pressure of P. It has a movable piston with an area of A that's open to the atmosphere. So that ensures that the gas cylinder is always under a constant pressure since it's open to the atmosphere. Oops. All right. So in that case, if the gas in the cylinder is heated, so again, when we're at constant pressure, but the volume can change, if the gas in the cylinder is heated, then it will expand to do work on the piston. So if the gas is heated, to keep that pressure constant, that volume is going to have to expand. And then that's going to do work on the piston. Since the pressure of the gas is P and the piston has an area A, then that means the force of the gas exerted on the piston is equal to P times A. And then recalling that work is force times distance. Remember that from a long time ago. Then the work done by the gas moving the piston from its initial position to its final position would look like this. Force times distance, but we know that force is equal to PA, so we put PA in there, and we use distributive property to multiply that through because the area is going to be the same for both, for the piston. The area of the piston before and the area of the piston after will obviously be the same. Okay. All right. As can be seen in the figure, the initial volume of the gas would be VI, which is equal to the area of the piston times how far it moves. The final volume is the area of the piston times where it, let me start over there. The initial volume would be the area of the piston times the displacement initially or where it started. And then the final volume would be the area of the piston times where it ended up. Okay, so we could also rearrange that equation and say that work is equal to pressure times the change in volume. So work done in a constant volume process equals the pressure times the change in volume. Okay, we're going to be looking at some graphs with these pressure volume graphs in just a minute too. All right, so here's an example. A gas with a constant pressure of 150 kilopascals expands from a volume of 0.76 meters cubed to a volume of 0.92 meters cubed. How much work is done? All right, so we're given the pressure and we're given the initial volume and the final volume, so we can very easily find work just by plugging into that equation. Okay, and you get 24,000 joules. All right. So here's our pressure volume graphs. All right, so a constant pressure process can also be represented graphically and on a pressure volume graph. So a PV graph, volume is always on the x-axis, pressure is always on the y-axis. So here would be an example. So if we have initial volume here, final volume here, and our pressure is constant, so we just made a box basically. And that's very, very easy to find the area under the curve, because the area under the curve is the volume. So the area of this shape here will be our volume. I'm sorry, will be the amount of work that's done. I don't know what I was thinking. The area under the curve is the work that is done. So what we need to do with that is just find the area of that shape, and that is equal to the work done. Okay. Notice that the shaded region below on the rectangle before, the height is P, the width is delta V. So if we do the area of that will wind up giving us work. This is true even if both the volume and pressure are changing. So the area under the curve, and that's important for you to remember because we know we have some problems with that. The work done by an expanding gas is equal to the corresponding area under the curve in pressure volume graphs. And y'all found areas under curves before at the very, very beginning of calculus. If you think way back to when you started calculus, that was probably one of the first things you did. You found the area under a curve. And you broke that area up into smaller and smaller increments of things like rectangles so that you could get to the limit and then and that limit, when you found the limit, would be the area under the curve. And that's about all the calculus I remember. So I won't be asking you any more of those questions. Probably even got that much wrong. But I do remember area under the curve having something to do with limits. All right, so moving on. A device for determining changes in atmospheric pressure is called a weather glass, and it's shown here. The air inside expands or contracts with changes in atmospheric pressure. This results in the change in the water level within the water glass. So changes in volume in the weather glass occur at a constant temperature of the room. So the change of volume doesn't necessarily mean that you've had a change in temperature. So a process such as this occurs at a constant temperature. So we've talked about constant volume, we've talked about constant pressure. So now in this particular situation, we're talking about a constant temperature process, and that's called an isothermal process. There are two processes we're going to talk about in this chapter, isothermal and adiabatic, and we'll get to that in a minute. But so make sure you're able to recognize which one is which. Isothermal means constant temperature. And obviously, if we have a constant temperature, we have a constant thermal energy. So there is no change in the thermal energy of the system when it's isothermal. So whatever you had to start with, that's what you'll have to end up with. because with isothermal, there is no change in the thermal energy. So what we do for that is we set delta E equals 0. And so there's our equation, our first law of thermodynamics. So if delta E is 0, and then we move Q to this side, we wind up with Q being equal to W. So for an isothermal process, the amount of work that's done is equal to the amount of heat that the process has. Work done by an isothermal process is equal to heat. So please make sure in this chapter that you're able to distinguish between these three and be able to match and determine the amount of work for each of those particular systems. So constant volume, constant pressure, and constant temperature, which is also called isothermal. Alrighty. And this is just giving you some more examples of those things. The figure below shows a plunger being rapidly pushed down into a cylinder in a device called a fire syringe. Because there is no time for the thermal energy to flow into or out of the system, the work done on the plunger increases the thermal energy in the system. The resulting increase in temperature is enough to ignite bits of paper at the bottom of the tube. A thermal process with no exchange of heat, so we're not having heat being put in or heat being given off, that's what we call an adiabatic process. So when the temperature stays the same, that's isothermal. When the heat, there's no exchange of heat, so when Q is 0, that is called an adiabatic process. This usually happens when you have a system that is very well insulated to keep heat from flowing in and out. The fire syringe illustrates a process that's also that might also be adiabatic, and it's adiabatic because it occurs so fast. There was no time for the heat to flow from one thing to another. All right, so the figure below, we see some different insulated cylinders. The insulation prevents thermal energy from going into or out of the system. So we see that it's insulated here. That means that if heat is not going into or out of the system, there's no thermal energy flow. So Q is 0, which means from the first law of thermodynamics, that means that the change in energy is the amount of work done. Okay, so again, make sure you have that written down somewhere, that in this situation where Q is 0, the first law of thermodynamics says the change in energy is then going to be equal to the amount of work that is done. So in an adiabatic process, if work is done on the system, now you've got to pay attention to your wording in these questions. We have work done on the system. Work is done on the system, then W is less than 0. Then the system's thermal energy increases, so delta E will be greater than 0. Similarly, if a system does work, then work is greater than 0, so its thermal energy actually decreases. Okay. So for an adiabatic process, if the work is done on the system, that means work is less than 0, work is a negative number. And so the system's thermal energy will increase. If the system does work itself, then its work is positive, and so its delta E, its change in energy, would be a negative number, be less than 0. Adiabatic heating and cooling can affect the climate of a particular region. For example, as moisture-laden air above the mountain slopes, the atmospheric pressure decreases, which allows the air to expand and undergo adiabatic cooling. The result is that the moisture in the air condenses to form clouds, as the one that's shown. Okay. So this adiabatic heating and cooling is responsible for weather patterns that we see. Second, third law of thermodynamics. Experience tells us that thermal energy always flows from warmer to cooler. So I think this is actually the third section in chapter 11. Let's see, where are we at? Okay, so I think we're starting the third section, which means I think I'm going to go ahead and close this video out and just do a video per section. All right, so make sure you've taken good notes, especially on these processes of constant volume, constant pressure, constant temperature. That would be isothermal and adiabatic, okay?